Welcome back. Problem 2.36. So in this problem, it is given that a 250 millimeter bar of 150 by 30 millimeter. So this is 15, not 150. So 115 by 30 millimeter rectangular cross section consists of two aluminum layers of 5 millimeter thick brazed to a center brass layer of same thickness. Clear? If it is subjected to centric force of magnitude 30 kilonewton, and knowing that modulus of elasticity for aluminum is 70 gigapascal and for brass it is 105 megapascal. So determine the normal stress in aluminum layer and in the brass layer. So from this figure 2.36 you can see this is a 250 millimeter bar having cross section, that is width is 30 millimeter and total thickness is 15 millimeter. So here above it is written as 150. This is wrong. This is 15 millimeter. Okay. So two layers aluminum layer. Top one and bottom one is aluminum while the middle one is brass. Clear? And this is subjected to load P that is applied 30 kilonewton. So we have been asked to find out the stress in brass as well as in aluminum portion. So let's start with the solution. Now you can see there are three layers and each layer having area A is equal to this width 30 multiplied by its thickness 5 millimeter. So you can see this is 5. So three layers are present. So for every layer this will be equal to square millimeter. Clear? So this area comes out to be 150 into 10 raised to power minus 6 square meter. In term of meters, it is 150 into 10 raised to power minus 6. Now you can see that due to this load P, clear, that is applied on this bar, each layer will take the load. Each layer, I will write each layer will take load due to P. Now we can say that PA is load taken by aluminum layer, load on each aluminum layer, and PB is load on brass layer. As due to this load P, there will be deformation in this bar, and that deformation will be equal to P into L divided by AE. Clear? For brass, this deformation is equal to del B, and that is equal to P brass into length divided by area of brass into modulus of elasticity of brass. And for aluminum layers, this deformation in aluminum will be equal to PA into L divided by A into EA. As the lengths are same and area, cross-sectional area of each layer is same, so I have generally write L and A. Now due to this load, the deformation in this bar is equal to deformation in brass is equal to deformation in aluminum, because they are glued together, so their deformation will be same. So it means that deformation in aluminum is equal to deformation in brass. Now you can put this aluminum deformation in aluminum is equal to P into L divided by A into EA, while deformation in brass is equal to PB into L divided by A into EB. Both L by A will be cancelled, and we can get PB is equal to this will cancel with this will cancel with this. So PB is equal to PA into EA divided by EB. Now you can put the value PB, PA is not known, EA is equal to 70 gigapascal and EB is 105. So 70 EA is 105. 105 E. Let me check. EA is equal to 70 and EB is 105. So this PB is equal to PA into EB. I have written wrong. This is EB while this is EA. So PA into 105 gigapascal. So 10 raised to the power 9 divided by 70 gigapascal. 10 raised to the power 9. It will cancel. So ultimately we will get PB is equal to 105 over 70. 105 over 70 PA. Or simply you can simplify it. PB will be equal to 1.5 times PA. Now you have this equation. You can now we know that due to load P due to load P, each layer will take the load, so total load will be equal to, there are two layers, you can see two layers of aluminum, so it will be equal to 2Pa plus Pb, which is the layer of the brass. So you can put the value of Pb, 2Pa is plus Pb is 1.5 times Pa. So total that is equal to P. So from here this P is equal to 3.5 Pa. And this Pa is equal to P divided by 3.5. Now P is given as 30 kilonewton. I will show you divided by 3.5. So this load P is 30 kilonewton. You can see this is 30 kilonewton. So from here you will get this Pa is equal to 8.57 kilonewton. So you can put it in this equation. So PB will be equal to 1.5 times 8.57 kilonewton, and you will get PB is equal to 12.85 kilonewton. That is PB. Okay, so this is your PA, this is your PB, and this was the relation between PA and PB. Now we will move toward finding our first part, that is sigma aluminium. So sigma aluminium, as the load is compressive, so minus Pa divided by area of aluminium layer. So you can put minus 8.57 into 10 raised to the power 3 divided by area, it was 150 into 10 raised to the power minus 6. So when you calculate it, it will be minus 57.1 into 10 raised to the power 6 Pascal. Or you can say that sigma aluminium is minus 57.1 megapascal. So this is your first part. Clear? We will move toward second part, and that second part is stress in bronze layer, and that is equal to minus PB divided by area of bronze layer. So minus PB is minus 12.8 into 10 raised to the power 3 Newton divided by area is same, because the cross-sectional area of each layer is same. So when you calculate it, it will be minus 85.7 megapascal. So sigma B is equal to minus 85.7 megapascal. So this is the answer of, sorry, this is the answer of sigma b is equal to minus 85.7 megapascal. So this is our main answer, and this is the one which is the required value. I hope it will be clear to you now. And if you have any question, you can ask me in comment section. Thank you for watching.